Welcome. Today we are discussing Module 3.2, Generating Embeddings Locally with HuggingFace and Sentence-Transformers, Practical. We'll cover loading local BERT models, vector extraction pipelines, and batch embedding optimization. Here's a quick look at where we are in our curriculum. Hello everyone, and welcome back to our series. Today, we are deep diving into the practical engineering steps behind generating high-quality vector embeddings right on your local hardware. In production corporate architectures, keeping customer data secure means minimizing external network calls to third-party APIs. By setting up a local HuggingFace or SentenceTransformers pipeline, you achieve complete data sovereignty, customized optimization, and virtually zero network latency. If you look at the architecture diagram on screen, you'll see how raw text undergoes tokenization, tensor conversion, encoder processing, and pooling layers to generate high-fidelity vectors. Don't worry about copying this down. You can check the link in the description to download the architecture diagram and script anytime. Let's start building. To kick off our implementation, we will use the SentenceTransformers library to initialize a local BERT variant. In the code snippet displayed on screen, notice how we import the SentenceTransformer class and specify the pre-trained all-mini-LM L6v2 model. This tiny yet powerful model provides an optimal trade-off between speed and semantic quality. When we execute this code, SentenceTransformers automatically detects our hardware, whether it is a CUDA GPU, Apple Silicon MPS, or standard CPU. Please check the link in the description to download the architecture diagram and script so you can run this script concurrently alongside me. Let's review the actual terminal logs from executing our initialization script. As we see, the model weights download dynamically on the first run and are cached locally. The output outputs beautiful 384-dimensional dense float arrays representing our input sentences. This shape is crucial. Every single sentence you process, regardless of length, will be standardized into a point in this 384-dimensional space, ready to be searched or compared. Sometimes, using basic wrappers isn't enough. As senior systems engineers, you will need to orchestrate raw tokenization, extraction, and tensor operations directly in PyTorch. In the code displayed on screen, we bypass the basic wrappers and instantiate the raw auto-tokenizer and auto-model directly from HuggingFace. We then write our own mean pooling function to aggregate individual word tokens into a unified sentence representation using the attention mask. Check the link in the description to download the architecture diagram and script for this precise low-level pooling implementation. Let's examine the output of our custom PyTorch pipeline execution. We loaded the raw tokenizer and deep learning model weights, parsed the token states, masked out pad tokens, and computed the normalized float tensor representation. As we can see in our log output, we get a beautifully normalized PyTorch tensor of dimensions 1 by 384, ready to be ingested in any production system. Let's step up our engineering game and move into high-performance batching. When handling large production datasets containing millions of log files or documents, generating vectors one by one is incredibly slow and inefficient. To optimize compute resources, we must utilize batched inference. On your screen, look at our script optimized for batch processing. Here, we dynamically inspect the device availability, shifting the workload to a CUDA GPU if present. We then configure the model's encode function with custom batch parameters and activate the progress bar tracker. Make sure to check the link in the description to download the architecture diagram and script for your own benchmarking. Let's review the terminal performance results of our batched execution script. Running our 5,000 sentence corpus in parallel batches of 128 items dramatically increased our computing speed. Instead of wasting processing cycles on sequential function calls, the tensor matrices were computed simultaneously. As a result, we reached an incredible throughput of over 1,200 sentences generated per second on a CUDA GPU backend. These optimization metrics are vital for modern production NLP applications. Fantastic job! Today we mastered how to load local BERT transformer models, perform custom mean pooling calculations on raw tensor states, and design a high-performance batched inference pipeline using HuggingFace and SentenceTransformers on local devices. But now that you have successfully generated millions of high-dimensional vectors, how do you perform ultra-fast searches across them at enterprise scale? You don't want to use standard relational databases for this task. That is exactly why you need to join me for our next upcoming lecture, Module 4.1, Introduction to Vector Databases, Theory, where we will dive into indexing algorithms, similarity metrics, and advanced vector storage engines. Make sure to download today's script and architecture diagram from the link below, subscribe to the channel, and I will see you in the next module.